In the last few lectures, we were discussing pressure driven flows, flows where the driving force is due to the pressure. The pressure, as I said, is a force that is exerted perpendicular to the surface in a flow. The pressure is non-zero even when the fluid is not flowing, and the pressure always acts perpendicular to any surface within the fluid along the inward unit normal. It is compressive. The magnitude of the pressure at every location is uniquely specified, and the direction of the pressure is always perpendicular to the surface with which it is measured. And what we are discussing in this course is the dynamical pressure, not the thermodynamic pressure. The thermodynamic pressure is an absolute pressure. It has 0 value at absolute 0 temperature, whereas fluid flows are driven by pressure differences. So, what matters as far as a fluid flow is concerned is the pressure difference between two locations and not the absolute pressure itself. Okay. And we had solved a couple of problems. One is the discharge from a tank. We had seen how to use the Bernoulli equation for this. And a second problem that we had solved was the pumping of water into a tank, which is sealed so that the air within the tank cannot escape as the tank is being as the water is being pumped into the tank. We will discuss another example of a Venturi meter, which is a contraction in a pipe. Pipe of diameter d, and I will call the cross sectional area of the pipe as AP, and the cross sectional area of the contraction is going to be called AC. The cross sectional area of the contraction is called AC. And obviously, as the water flows through, the streamlines have to bend as it goes through the contraction. Since the cross sectional area is lower in the contraction in comparison to the rest of the pipe, the velocity is higher. The flow rate has to be the same between the contraction and the pipe at steady state. Therefore, if the flow if the area is smaller, the velocity has to be higher. And there are usually pressure tappings which record the pressure difference between the contraction and the pipe. So, as you know, these pressure tappings are basically what are called manometers, and these contain a liquid, water if the pressure difference is small, mercury if the pressure difference is large. And the pressure difference is basically given by measuring the height difference between the two arms. When the pressure is higher, the height in that arm will be lower, and the pressure is lower, the height will be higher. So, it is basically obtained by measuring the difference in height between the two arms using a manometer or by some other pressure measuring device. Now, how do we calculate the flow rate just from knowing this pressure difference delta P? We know that the total flow rate has to be the same, the volumetric flow rate, which is the velocity in the pipe times the area, cross sectional area of the pipe, has to be equal to the velocity in the contraction times the cross sectional area of the contraction. The velocity has to be the same on both sides. And what that means is that the velocity in the contraction is equal to the velocity in the pipe times the area of the pipe divided by the velocity in the area of the contraction. Okay. So, this emerges just from volumetric conservation. Okay. Okay. So, this emerges just from volumetric contraction. The second thing that we will do is to write the Bernoulli equation between these two locations, the pipe and the contraction. Okay, the Bernoulli equation between these two locations, the pipe and the contraction. It should be noted here that the velocities have to be considered as some kind of averaged quantities in this case. Okay. This is valid at high Reynolds number, and we are not making including viscous effects here when we calculate the pressures. Okay. And therefore, these have to be considered as inviscid flows. Okay. And these are valid only when the Reynolds number based upon the pipe velocity and diameter as well as the contraction velocity and diameter are both high. Okay. So, it is only in that limit that this formulation is applicable. So, the pressure in the pipe is Pp say, and Pc is the pressure in the contraction. Okay. Then from the Bernoulli equation, if I assume there is no height change between the pipe and the contraction, that is that this is horizontal, then P pipe, okay, plus half rho V pipe square is equal to P contraction plus half rho V contraction square. Okay. So, into V contraction square minus V pipe square. Okay. And I can substitute this for this expression for the velocity in the contraction. Okay. So, this is going to be equal to half rho into V pipe square into A pipe by A contraction the whole square minus 1. Okay. Okay, so, that is the formula. Okay. And the left side is just this pressure difference delta P. Okay. The left side is just this pressure difference delta P. Okay. Therefore, from delta P I can find out what is V pipe. Okay. I can find out that if I solve this equation, I can get V pipe is equal to 2 delta P by rho into A P. Okay. The square root of. Okay. Okay, so, that is the final expression for the Venturi for the velocity in the pipe, okay, from the pressure difference. So, by measuring this pressure difference, I can calculate what is the velocity in the pipe. Okay. Okay. So, let us consider a concrete example. Okay. If I have a Venturi meter with contraction of diameter 1 centimeter, okay, in a pipe of diameter 2 centimeters. Okay. Okay, so water of density 10 power 3 kg per meter cubed flows in the pipe. And delta P, the difference in pressure between the contraction and the pipe, is equal to 30 kilopascals. Okay. What is the flow velocity? Okay, for these particular values. Okay. So, the flow velocity has to be equal to square root of 2 delta P by rho into A P by A C the whole square minus 1. Okay. In this particular case, a pipe by a contraction, okay, is equal to pi into 2 centimeters square, 0.02 meters the whole square by contraction, which is pi into 0.01 meters the whole square. Okay. So, this is equal to 4. Okay. Okay, so, this is equal to 4. Okay. So, this becomes equal to square root of 2 into 30 into 10 power 3 pascals, 30 kilopascals. Okay. Divided by 10 power 3 kg per meter cubed is the density of water. That is the density of water, and AP by AC the whole square minus 1. So, I get 16 minus 1. Okay. AP by AC is equal to 4. So, AP by AC the whole square is equal to 16. Okay. And you can easily simplify this, these two will cancel out. Okay. I have a 15 in the denominator. So, I just get a value of 4, square root of 4 meter square per second square. So, this just becomes equal to 2 meters per second. Okay. So, that is the flow velocity. Having got this flow velocity, one has to go back and verify that the assumptions that were made in deriving this flow velocity is correct. Okay. The assumption made is that it is an inviscid flow. That is valid only when the Reynolds number is high. Okay. So, the Reynolds number for this case is equal to rho V pipe times the D pipe by the viscosity. Density of water is about 10 power 3 kg per meter cubed. Into the velocity is 2 meters per second, into the diameter of the pipe is 2 into 10 power minus 2 okay, meters. 2 centimeters is the diameter, 2 into 10 power minus 2 meters, okay, divided by the viscosity. Viscosity of water, okay, is 10 power minus 3 kg per meter per second. Okay. Okay. And this you get it as 4 into 10 power 4 in this case. Okay. So, therefore, the Reynolds number is high, and therefore, you can use this formulation. Even though strictly speaking there is this will be a turbulent flow. So, it does not strictly speaking satisfy the potential flow condition, but nevertheless this formulation gives you an accurate measurement or gives you an estimate for what is the velocity and thereby what is the flow rate. The flow rate is the velocity times the cross sectional area of the pipe. Okay. So, I have shown you how to use a Venturi meter. Let us look at another example, okay, which is the flow over a wire. Okay. So, typically what happens is that if you have an open channel like a canal or a stream, okay, in which water is flowing, okay, and you want to know what is the flow rate of water in that canal or in that stream, okay, you can put in an obstruction in the flow in the at the bottom. Okay. So, if this is the water that is flowing, okay, let us say, okay, you can put an obstruction, okay, that looks something like this. Okay. Okay, an obstruction that looks something like this, so that the water level upstream will the water will collect upstream, and the water level as it goes across will decrease. Okay. So, this is the obstruction, okay, with height h, which is a function of the downstream distance. Okay. The height of this obstruction is a function of the downstream distance. Okay. This is what is called a broad crested. Okay. Okay. You could also have a sharp crest. Okay. For example, you could have something that looks like this, okay, in which case you will have the velocity, the interface coming down like this. Okay. So, okay, where this is the maximum height, okay, h c, and the maximum height in this case is h c. Okay. And now, we would like to find out what is the flow rate in this, okay, due to the of the water that is flowing, and in order to find out the flow rate we have put in an obstruction. Okay. It turns out that the flow rate can be calculated just from the height, okay, the height of the water level above this, okay, the height d of the water level above the point at which the height of the wire the obstruction is a maximum. Okay. So, at this maximum location, if I find out what is the height of the water above this just by inserting a rod, say, and finding out how much gets wet, from that I can calculate what is going to be the flow rate and the velocity past this. Okay. So, I will show you how to do that. Okay. So, first thing I will do is to draw a more accurate figure, okay, for this broad crested wire itself. Okay. Okay. So, this is the bottom surface, okay, and this is the obstruction that is placed. Okay, this is the obstruction that is placed, and this is the level of the water above this. Okay. This is the level of water. Okay. So, far upstream the level of water goes to a constant value. Okay. You get a constant surface far upstream, where the velocity is small, because the height of that water layer water stream is large, and that location the velocity is smaller than what it is at, as it is crossing the wire. Okay. So, in this region, okay, where the height of the obstruction is a maximum, okay, that is where you would expect the velocity also to be large. Okay. Therefore, in the upstream region, the velocity I will call it as the depth in the upstream region. Okay. du is the depth of this channel upstream of the obstruction. Okay. Okay. Depth is depth of the channel upstream of the obstruction. Okay. This thing I will call it as the maximum height as h c. Okay. The maximum height of the obstruction as h c. Okay. And therefore, the difference, this difference is going to be equal to du minus h c. Okay. That is going to be the difference, du minus h c. Okay. Okay. And this height here, okay, so this depth at different locations, okay, this depth at different locations I will call it as d. Okay. The depth of the water above this obstruction I will call it as d. Okay. And this is okay, d at the location where there is a maximum. Okay. This is d at the location where the height of the obstruction is a maximum. Okay. So, therefore, if I write the Bernoulli equation between this location and this location, okay, you can see that at this location the velocity at this location far upstream, the velocity is small because there is no obstruction there. Okay. The velocity is much smaller than the velocity as it goes above the obstruction, because as it is going above the obstruction, the depth of the water decreases and therefore, the velocity increases. Okay. So, if we assume that the velocity is 0 far upstream, okay, if we assume that the velocity is 0 far upstream and write the Bernoulli equation between this location and this location. Okay. So, far upstream, okay, I have P atmosphere plus rho g times du, okay, at the location far upstream. Okay. At this location the velocity is non-zero. Okay. So, I have here the pressure at the surface is just still P atmospheric pressure plus rho g into d plus h, I am sorry, hc, yeah, d plus h, okay, where h is the height, okay, h is the local height, okay, at a particular stream wise location, okay, plus half rho v square, where v is the velocity with which this water is flowing over the obstruction, okay, plus half rho v square. Okay. That is going to be the Bernoulli equation between this cross section and this cross section. Okay. So, that is going to be the Bernoulli equation written between these two cross sections, and I can cancel out the atmospheric pressure at these two locations, okay, and I will get du minus d, okay, minus h, okay, is going to be equal to half v square by g. Okay. Okay, that is the relation I get by dividing throughout by rho times g. Okay. So, this is equal to v square by 2g. Okay. Therefore, the velocity v is equal to square root of 2g into du minus d minus h. Okay. This relationship is valid at any cross section. Okay. This relationship is valid at any cross section. Okay. At any cross section this relationship is valid, because I take the local depth d and the local height of the obstruction. The depth is measured above the obstruction. Okay. So, I take the local depth and the local height above the obstruction, and I get this relationship for the velocity. Okay. And the volumetric flow rate per unit area, okay, the volumetric flow rate per unit area perpendicular to the plane. Okay. I assume that there is a channel whose width is larger than the height, okay, as you would see in most terrestrial situations. This volumetric flow rate is equal to the depth times the velocity. Okay. So, it is the product of the local depth d and the local velocity with which it is flowing. Okay. So, I can write this upstream distance minus h, okay, is equal to du minus d minus h plus d. Okay. So, the right side the d's just cancel out and you get the left side. Okay. On the right side for this one I can substitute from here, okay, to get v square by 2g, okay, and for the second one I can substitute from here, okay, to get, okay, plus V dot by V square, I am sorry, plus V dot by V. Okay. Note that this du minus h, okay, is basically the total depth du minus h, right. Minus h is the local height at any streamwise location along the wire, okay. H is the local height, okay. And du minus h passes through a minimum when h is equal to hc, okay, the maximum height, okay. When h is equal to hc, okay, note that du is the total height, that is a constant. H is the height of the obstruction, okay. H is the height of the obstruction, okay. Therefore, du minus h is a minimum when the height of the obstruction is a maximum, okay. Du minus h is a minimum when the height of the obstruction is a maximum, okay. So, du minus h, the derivative with respect to the streamwise direction, goes to 0 where h is a maximum, okay. And therefore, d by dx, okay, if I take this as the x direction of du minus h, okay, that has to be equal to 0 when h is equal to hc, okay. And if I use the right side of this equation here for du minus h, where the velocity v, I made a mistake here, this should be the velocity v, okay. This should be the velocity v, kindly correct that, okay. If I use that on the left side here, so this is equal to v by 2g minus v dot by v square, okay, times dv by dt dx, where dv by dx is the variation in velocity along the x direction, okay. And at the point where it is a maximum at h is equal to hc, right, this implies that this has to be equal to, this right side has to be equal to 0 at h is equal to hc, okay. This right side has to be 0 at h is equal to hc, which means that, okay, at h is equal to hc, okay, the maximum height, okay, v is equal to v dot times g whole power 1/3. Okay. You can just solve this equation quite easily. There should be no 2 in the denominator, because when I take the derivative of v square, I will get 2v. Okay. So, it is just v by g minus capital V by v square, and from this you will get this relationship. Okay. And substituting this expression for v into this relation, okay, into this relation, okay, substituting this expression for v into this relation, I get du minus h, okay, is equal to v square, that is v dot g power 2/3 divided by 2g plus v dot by v dot g whole power 1/3. Okay. And you can easily simplify this to get 3 by 2 into v dot by g, okay, whole power 1/3. So, that is the volumetric flow rate, the relationship between the volumetric flow rate, okay, per unit length perpendicular to the plane, okay, the relationship between the volumetric flow rate per unit length perpendicular to the plane, and this height, okay. At h, I told you that this is valid at h is equal to hc. So, the left side is du minus hc, okay. Okay. So, just by knowing this height here, okay, just by knowing the difference in height between the water level far upstream and the maximum height of the obstruction, I can find out what is the volumetric flow rate. Okay. So, I can just solve this to get, okay, v dot is equal to 2 by 3 whole power 2/3, okay, into g power half into du minus h whole power 3 by 2. Okay. So, knowing what is the depth. Okay. So, this should be Hc because that is the maximum height of the crest. That is Hc, which is the maximum height. So, just by knowing what is the maximum height of the water far upstream above the maximum height of the obstruction, what is the difference between the height of the water far upstream or the fluid far upstream and the height of the obstruction, I can find out what is the volumetric flow rate per unit length perpendicular, multiply that by the width, okay, in order to get the total volumetric flow rate. Okay. So, this is another example of how the Bernoulli equation can be used for metering of flows, for determining what is the velocity or the volumetric flow rate. So, I will continue this in the next lecture, where we will look at a couple of more applications before we go to a laminar flow in a pipe. Okay. So, we will look at a few more applications of the Bernoulli equation and then proceed to the laminar flow in a pipe. I will continue this in the next lecture. Okay.